Okay, hello everyone in a new video. So we have reached part 5 of chapter 8, which is the chapter of Newton's second law for rotation. Now we'll complete solving exercises. Exercise number 6, homogeneous and uniform rod BC of center G. Now here let me make it clear that homogeneous means that it is made, the mass is distributed uniformly along its length, which means the center of gravity G will be at the midpoint of BC. So if the length of BC, which is given by L, is given to 1 meter, this means that BC is equal to 1 meter. This means that BG is equal to GC is equal to 1 divided by 2. This means 0.5 meters. And its mass is given by M is equal to 10 kilograms, the mass of the beam. Now a small is attached to a pole by a hinge at point B. So this is the hinge here. So the moment here we have a reaction. Now a small mass M is equal to 5 kilograms is connected to C by a massless wire. The system thus formed is maintained in equilibrium, and by equilibrium it means we can use rotational and translational equilibrium. And previously we have justified why we will start with the rotational equilibrium in order to determine the reaction that is at point B. Then after that we can determine the reaction using Newton's second law for translation, which is equilibrium condition but for translation. The system thus formed is maintained in equilibrium by using a metallic massless string AG, as shown in the adjacent figure. Take G is equal to 10 meters per second square. Note ABG is an equilateral triangle. Then this angle is 60 degrees, this is 60 degrees, and this is 60 degrees. No need for this angle. Now number 1, list the 4 external forces acting on the rod. We have the tension and the string here T1, say, the tension T2 here, the reaction. We suppose that the reaction is something like this. So these are 3 forces. The additional force, which is the weight of the beam, which is vertically downward like this. Now let me do the reaction to be something like this, just to make the figure clearer. Then we have the tension T1, tension T2, and the reaction R at the hinge. Now here I'm not specifying what does each one represent because I have listed them on the figure. I mean the tension T1 by this string, tension T2 by the metallic string, R at the hinge, etc. And the weight W of the beam. So here why we didn't consider the weight of this mass, because it is already included in this tension. We cannot consider the weight and the tension at both times because we can detach the system like this, and we consider only the forces that are acting at this system. Now number 2, determine the tension in the string GA. So we need to determine this tension. Now for sure we will start by the sum of moments, then we need to calculate the moment of each force. So we know, the reaction will not be included. We know the moment of W because we know the magnitude of W and we know the distance. Now here the axis of rotation, always the beam will rotate around the hinge, so this is the axis of rotation delta passing through B. Even if they didn't specify, but also always the beam can rotate only around the hinge, which is the axis of rotation. Now the reaction will not be included. We know the weight. We will determine T2. So it is left in order to determine T2 to determine T1. So first we'll apply translational equilibrium on this solid. Then after that we will determine T1. Then T1 will be included in the sum of moments is equal to 0. So here we have another one, T1 prime. So because I have included vectors, I have differentiated between T1 and T1 prime. In magnitude, T1 prime is equal to T1, but as forces, no. For this reason, I have placed the prime. So first, let me say at equilibrium, and here I'm talking about translational equilibrium for the small mass. So the only two forces acting on the small mass are given by the weight plus T1 prime, which is equal to 0, which means that W is equal to minus T1 prime. Here, this is a vectorial equation only consisting of two vectors, no need to project. Then in magnitude, we have that W is equal to T1 prime, but we know that the magnitude of W is given by M multiplied by G. Here we are talking about the small mass, which is 5, multiplied by 10 equal to 50 newtons. Then T1 prime is equal to 50 newtons, and it is equal to T1, the string is inextensible. So we have that T1 is equal to 50 newtons. Now let's proceed with the sum of moments. Then in order to calculate the sum of moments, we need to calculate the moment of each force acting on the beam. Then the moment of the weight around delta is equal to the tangential component multiplied by the distance. Here recall that this distance represents the distance from the point of application of the force to the axis of rotation, which is BG, from the axis of rotation of the beam, which is BG, equal to 0.5 meters. Now, the tangential component of W can be determined by the tangent to the radial direction. This is the radial direction. Then the tangential direction will be something like this. Now, okay, so this is the positive direction of rotation. Then the weight around delta will try to rotate the system like this, so it's negative in the negative direction multiplied by W multiplied by the cosine of this is the tangential direction, this is W, so multiplied by the cosine of this angle. We need to determine this angle. So here, if this line, which is the vertical, parallel to this line, which is the vertical, so if this is 60 degrees, then this is the 60 degrees, alternate interior angles. If this is 60 degrees, then this angle will be 30 degrees. Okay. Also, this can be determined using another way. So if you complete this triangle, this will be 30, this will be 60, which means this is 60, so this is 30. So you can determine this angle in any way that you want. So the moment of the weight around the axis delta is equal to minus W cosine 30 multiplied by D, which is BG. So minus, here we are talking about the mass of the beam, which is capital M multiplied by G cosine 30 multiplied by D, then minus 10 multiplied by 10 cosine 30, I think it is radical 3 over 2, now I will check, and multiplied by 0.5. Indeed, multiplied by 0.5 multiplied by 10 multiplied by 10, which is equal to 25 radical 3 Newton meter. So the moment of the weight around the axis delta is equal to minus 25 radical 3 Newton meter. It is left to determine the moment of three forces. Now let's proceed with the tension T1, which is equal to T1 tangential multiplied by D, and in this case D represents the distance between the axis of rotation and the point of application of the force, which is BC, which is equal to 1 meter. Now T1 tangential, notice that T1 is in the same direction of W, which will be negative because it will try to rotate the system in the negative direction, multiplied by the magnitude T1 multiplied by the cosine of the angle. This is the radial direction, and this is the tangential direction. So this line is parallel to this line, and they have this line in common. So as a corresponding angles, this is 60 degrees. Then this angle here, it is given by, so this is 30 degrees. So cosine 30. Therefore, the moment of the tension T1 around delta is equal to minus T1 cosine 30 multiplied by BC, which is equal to minus 50. This is T1 multiplied by radical 3 over 2 multiplied by 1, which is equal to minus 25 radical 3 Newton meter, because this with this give us 25. Now as for the moment of T2 with respect to delta is equal to T2 tangential multiplied by D, in which D is equal to BG is equal to 0.5 meters. So T2 tangential, notice that T2 will try to rotate in the positive direction, which is plus. Now the magnitude of T2 is unknown because we are interested in determining the tension in the string GA, and so it is T2 multiplied by the cosine of the angle between T2 and the tangential direction, so this is 30, which is equal to radical 3 over 2 T2. So the moment of T2 around delta is equal to radical 3 over 2 T2 multiplied by the distance T, which is BG, which is 0.5. Okay, so 0.5 times 0.5, 0.025, I think. 0.25 radical, so it is 1 over 4 multiplied by T2. So now we can say that the sum of moments around the axis delta is equal to 0 because it is in rotational equilibrium. Let me say at rotational equilibrium. We have that sum of moments around delta is equal to 0. We have the moment of W around delta plus the moment of the tension T1 around delta plus the moment of the tension T2 around delta is equal to 0. Now the moment of the weight is given by minus 25 radical 3 plus the moment of the tension T1, which is given by also minus 25 radical 3 plus the moment of the tension T2, which is given by radical 3 over 4 T2. So I have anticipated the fact that radical 3 will be a common factor, so we can directly remove radical 3, and here we can simplify by radical 3 because this is 0. So minus 50 is equal to minus T2 divided by 4, then T2 is equal to 200 newtons. So, and T2 must be positive because the chosen direction of the tension T2 is correct. So T2 is equal to 200 newtons. Now as for number 3, to determine the reaction R of the axis B. So now the reaction, okay, previously I didn't specify here, let me specify it, that also we have here the moment of the reaction R around delta, but the moment of R around delta is equal to 0, line of action of R passing through delta, so it is given by a radial direction and you don't have any tangential direction. Now we need to determine the reaction R of the axis B. So, and this can be determined using the translational equilibrium. Then at equilibrium, now here determine the reaction, let me say all the properties. Let me write it in black, just to indicate that this is part of the question. All the properties of R. So we will determine R in the vector notation. Once we determine R in the vector notation, we can determine all the properties of R. So we will say that sum of forces is equal to 0. Now notice that here I'm calculating R independent without referring to the figure. But the only thing that I will do is to consider this is the positive axis like this, and the positive y-axis like this. Now the different forces acting on the system are given by the reaction tension T1 plus tension T2 plus the weight equal to 0 vector. Now to deal, we are interested in R, so we need to determine Rx and Ry, and this can be done by projecting once along the X and once along the Y. Projection along the X-axis. So because we will project, let me determine the projection of each force. Let me start by the weight W. Then we have tension T1, tension T2, the reaction R. No need to determine Rx and Ry because we know nothing about them. We will calculate them explicitly referring to this equation. As for the weight, Wx is equal to 0 and Wy is completely minus W. Tension T1x is equal to what? Is equal to 0 and T1y is equal to minus T1. As for T2, T2 lies in the xy plane. So if this is the horizontal, the x component will be, it's pointing in the negative direction, minus T2 cosine 60. As for the y direction is given by, so if this is 60 degrees, then between the vertical, now I have noticed that I have done a mistake in the previous part. Or no, it's not a mistake. Okay, this is not cosine 60 because, okay, So I'm done with all the angles. Let me erase everything just to make it clear. Okay, and let me remove all of these data. Okay, so this will be the horizontal, and this is the vertical. Now here, if this is 60 and this is 90, because this is the horizontal and this is the vertical, they are perpendicular, then let me see. Okay, yes, true. Then this angle here will be given by 30 degrees. If this is 30 and all of this angle is given by 60, then this angle here that I'm shading will be 30 degrees, because it is the angle corresponding between the vector T2 and the horizontal, which is this. Let me repeat. Now here, what do we have? This 60 degrees corresponds to the angle between this one and this one, okay? But we are interested in projecting T2 along the x direction, which is this, and along the y direction, which is this, okay? So projecting T2 along the x direction requires us to determine this angle, okay? How do we determine this angle? If this is 60 degrees and this is 90 degrees, then this angle will be 30. So what is left from the 60, if we remove 30, then this is 30. Okay, so it will be minus T2 cosine 30. As for T2y, so as we have mentioned, if this is 30, then this is simply 60. And it is plus because pointing in the positive direction. Now let's proceed. Projection along the x-axis give us Rx plus T1x plus T2x plus Wx equal to 0. This is 0. Rx is equal to minus T1x because we want to determine this, plus minus T2x equal to T1x is 0, and minus T2x minus with minus becomes plus T2 cosine 30. T2 is given by 200 cosine 30 radical 3 over 2, so this is equal to 100 radical 3 newtons. Now projection along the y-axis, so we will drop down the vector quantities. Each vector quantity will carry the label y. This is Rx. What about Ry? Plus T1y plus T2y plus Wy is equal to 0. So Ry, T1y is minus T1, T2y is plus T2 cosine 60, and minus W, which is equal to 0. Then Ry is equal to T1 minus T2 cosine 60 plus W, which is equal, now T1 is given by 50, T2 minus 200 times half plus W, I think W is given by 100 because 10 multiplied by 10, it will be given by 100, so 10 multiplied by 10. Then this is 100, minus 100 plus 50 minus 50, So plus 100, this is equal to 50 newtons. So Ry equal to 50 newtons. Now so the vector R is written as 100 radical 3x, I, plus 50j. Now how can one interpret this result? Before interpreting, let me determine the magnitude. R in magnitude is given by square root of Rx square plus Ry square equal to 100 radical 3 to the power 2 plus 50 to the power 2, which is equal to so 180.27 in newtons. As for the direction, we determine tangent theta, which is equal to Ry divided by Rx, equal to 50 over 100 radical 3. Then in this case, theta is given by tangent minus 1 of 50 over 100 radical 3, and this is equal to almost 16.1 degrees. Now how do we interpret this result and check if it's correct or wrong, because in the previous part I have done a mistake regarding this. So before we calculate R, one can anticipate the direction of Ry. So if this is the tension T2 acting like this is the tension T1 acting like this, and this is the weight acting like this. Now if you join all the vectors on one point, if you consider one point, so suppose they are acting all of them on one point, then the weight will be downward like this. The tension also will be downward. So suppose that this is the weight, this is the tension, and the tension T2 is something like this. Now in order to balance the effect of these forces and for the beam to be at equilibrium, so what will be the direction of the reaction? It will be simply like this. Something like this. No, not like this. Let me be specific. It will be, yes, it will be something like this. Why? Because these two, if you add them, as if imagine, okay, so in order for these forces to balance each other, the logical direction of this force R to be something like this, because this will move downward. Okay, how I know that it will be something like this? Consider the following. So the only x component is given by T2x. So in order for this x component to be cancelled, you must have an Rx which is exactly equal to T2x, and this is what we have calculated from this equation. Okay, so the x component of R must completely oppose T2x. So first of all, my drawing is wrong, and if this is, for example, 1 point something division, this must be 1 point something division. So it must be like this. Now what about the y component? So this projection, which is Ry, must completely cancel the sum of these two. So this is 2 and 2.5, so they add up to 4.5. So they must completely cancel these 4.5 that I have represented here. But not worrying about all of these, this is just a discussion about if our answer will be correct or no, how one can check the answer. Now getting back to the figure, and if you want to plot Rx and Ry according to our values, so we know that it will be something like this. And indeed, if you check, Rx is positive and Ry is positive, which means that it will be something like, so if this is Rx is positive and this is Ry is positive, then the completion of this will be R, which is acting in this direction, which means it is correct. Okay, so what does this angle theta represent? It is the angle that the R vector makes with the horizontal direction. So this is theta, which is equal to 16 point something, and the length of this vector is given by the magnitude, which is equal to 180.27 newtons. Now moving to exercise number 7. So a 10,000 Newton shark is supported by a cable attached to a 4-meter rod that is it must be pivoted at its base. So this is also a hinge, so this beam can be rotated around this hinge. Neglect the weight of the rod. Number 1, they are telling us to calculate the tension in the tie rope between the wall and the rod if its holding system in position shown in the figure. We need to calculate this tension between the rod and the wall, which is T2. Suppose this is T1, this is T1 prime, and here we have the reaction, something like this, say for example, and the weight in the beam. So they are telling us neglect the weight of the rod, so the rod is massless. Okay, so in order to determine the tension in the rope between the wall and the rod, we need to use the sum of moments, because always we proceed in the sum of moments, because directly the reaction will be eliminated. Then we will proceed in the translational equilibrium. So what are the forces acting on the rod in this case? We have the tension T1 and the tension T2. These are the only forces that produce moments. Now we know we don't know the value of T2 because we want to determine it. It's left to know T1. T1 can be determined by the equilibrium on the shark. So at equilibrium, we are talking about the shark. So notice that here 10,000 newtons, which means 1,000 kilograms. If we divide by 10, I don't know if the weight of if the mass of the shark is worth 1 ton. You can check on Google. So if this given is correct or not. Here we are talking about the shark. Then the weight of S of the shark plus T1 prime is equal to 0 vector. This is the weight of the shark. So Ws is equal to minus T1 prime. In magnitude, T1 prime is equal to Ws, which is equal to 10,000 newtons. T1 is equal to T1 prime in extensible string. Even if not mentioned, we are not able to solve the exercise unless the string is inextensible. Now let's determine the moment of these two forces. Let's start by the moment of the tension T1 around the axis delta, pivoted here around the hinge. So it's given by T1 tangential multiplied by the distance d, in which the distance d is the distance from the axis of rotation to the point of application of T1. In this case, this is the length of the rod, which is given by 4 meters. T1 tangential is equal to, if this is the positive direction, T1 will try to rotate the system in the negative direction. Cosine of the angle between the tangential direction and the radial direction. This is the radial direction. This is the tangential direction. So for sure we need to refer to this triangle. If this is 60 and this is 90, then this will be 30 and this will be 60 degrees. So the angle between T1 and the tangential direction is 60, which is equal to, okay, no need to complete it here. Now this is equal to minus T1 cosine 60 multiplied by D equal to minus T1, which is equal to 10,000 multiplied by half multiplied by 4. So this will give us 2. So this is equal to minus 20,000 newtons meter. Okay. Now as for the moment of the tension T2, in which T2 will appear explicitly as an unknown, is equal to T2 tangential multiplied by D. D is the distance between the axis of rotation and the point of application of T2. So in this case, it's the length of the rod, which is 4 meters. T2 tangential, it will try to rotate the system in the positive direction like this. So it's a plus, multiplied by T2, which is kept as an unknown, multiplied by the cosine of the angle. So notice that T2 is completely lying along the tangential direction, so no need. No need for any projections. Now let's fit both quantities in the rotational equilibrium at rotational equilibrium of the beam. So we have that the sum of moments around the axis delta is equal to 0, which means that the moment of the tension T1 around delta plus the moment of the tension T2 around delta is equal to 0. The moment of the tension T1 minus 20,000 plus T2 multiplied by the distance D, because notice that this is T2 and this is the distance D, so multiplied by 4 is equal to 0. What's the type of this equation? Linear equation. Then T2 is directly given by 20,000 divided by 4, which is equal to 5,000 newtons. I mean 5,000 newtons, it is comparable with this, so it is the half, so I think the answer is reasonable. I'm not checking my answers with the answer key that I have, okay, but I suppose it is correct. So T2 is equal to 5,000. Now we are ready to find the horizontal, the horizontal and the vertical forces on the base rod. So number 2, for sure here we need to apply the translational equilibrium. Sum of forces is equal to 0 vector. Then the reaction plus the tension T1 plus the tension T1 prime, the tension T2 equal to 0 vector. We are interested in determining R. So projection along the x-axis. So Rx plus T1x plus T2x equal to 0. Let's determine the projection of each force. Rx, no need to determine it, keeping them as unknown. T1, T1x and T1y, T2, T2x and T2y. Now T1x, notice that T1 is completely vertical, so this is T1 if this is the positive direction of x and this is the positive direction of y, and T1y is given by minus T1. As for T2x, along the x-axis, so it is in the negative direction, minus t2 cosine 20. And what about t2y? So if this is 20, then this is given by 70 degrees, so plus t2 cosine 70 degrees. Now Rx plus 0 minus t2 cosine 20 degrees is equal to 0, which means that Rx is equal to t2 cosine 20. The value of t2 is given by 5000 times cosine of 20 equal to, let me check it again. So 4000, so times cosine 20, 4698.46 newtons. As for Ry is equal to T2, projection along the y-axis, drop down vector quantities, each vector quantity will carry the label y. So Ry is equal to minus T1y minus T2y. Recall that this beam has no mass. Minus T1y, so it will be plus T1, and minus T2y, which will be minus T2 cosine 70. Now here we expect that this, okay, we don't know anything. This may be positive or negative, okay? It's not a rule here, because the sign of R, the sign is included inside Ry. This is a component. It may be positive or negative. But later, okay, so here what will happen if this is acting like this and this is acting like this? What will cancel these two forces is something like this. So Rx and Ry must be positive. Now referring to the figure, so here we expect that Ry must be positive. T1 is given by 10,000, I think. Yes, this is T1, which is due to this weight. Minus 5,000, yes, multiplied by cosine 70. On the calculator, this is equal to, so as expected, 8,289.89 newtons. So these are the horizontal and vertical forces exerted on the base rod, on the base of the rod. So now R can be written in a compact notation, which is the vector notation, which is given by R equal to Rxi plus Ryj, which is equal to 4,698. I don't remember whether this is 46 multiplied by the unit vector I plus 8,289.89 multiplied by the unit vector j. And if you want to determine the magnitude, R is equal to square root of Rx square plus Ry square. And if you want to determine the angle, tangent theta is equal to Ry divided by Rx. This angle theta will be the angle between the vector R and the positive x-axis, like this. And this is the length, which is the magnitude. So that's it for me in this video, guys. In the next part, we'll complete the explanation of this chapter.